We're doing electromagnetic theory, and in this session we're going to talk about Gauss law and its applications, Ampere's law, as well as displacement current. So before we understand Gauss law, we need to understand what is electric flux. So a simple crude definition of electric flux would be electric lines of force emerging out of a given area, or maybe they could be going in, and accordingly the flux would be positive or negative. But that's just a theoretical definition. A more practical mathematical definition of flux is it's the surface integral of electric field over a complete surface area, and that can be represented by this loop integral. Of course, here in the graphic it's not looking like a loop, but this is a loop integral of E dot ds. E dot ds is the dot product of electric field and the area. Now this should be equal to the flux, the total flux emerging out of a given volume across the surface which is bounding the volume should be equal to 1 by epsilon 0 times the charge enclosed within the volume. And this epsilon 0 is also called the permittivity of free space, and it has a value of 8.85 into 10 to the power minus 12. Of course, the units can be also the dimensions of epsilon 0 can be obtained from Coulomb's law, as we had done in earlier classes. Well, this is the Gauss law, and the exact statement is the total flux emerging out of a closed surface is 1 by epsilon 0 times the net charge enclosed within the volume bounded by the surface. Now here the important point to note is that the charge should be enclosed within the surface, because if the charge is outside the surface, it would not contribute to any flux emerging out of that volume. So we'll find a simple way to prove Gauss law, and this could be done using a point charge. So let there be a point charge placed at the origin. So the position of this point charge would be in Cartesian coordinates 0, 0, 0. Now we create a hypothetical surface around this charge according to the symmetry of the situation. You can see if we talk about the electric field lines due to a point positive charge, then they emerge radially outward. So the symmetry of the situation demands that we have a spherical surface, the hypothetical surface that we are going to make to calculate flux. We also call it the Gaussian surface. So let's create a sphere of radius r around this charge with the charge at the center. Of course, the center is also the origin. Now the direction of electric field due to this charge, if you take a small area, infinitesimally small area ds shown here in this diagram, if you take this area and if you look at the field coming out of this area, since the field is radially directed and the surface normal of this area is also radially directed, we can clearly see here that the field and the surface are at 0 degree to each other. The surface normal and the direction of the field, they are in the same direction. So the angle between them is 0. So the flux reduces to just the product of the magnitudes of the electric field and the area, the small area ds, EDS, because cos 0 is 1. Now if we want to find out the net flux across this complete surface, then we take the surface integral of EDS. Electric field due to a point charge is 1 by 4 pi epsilon 0 r square times q, the charge, and if this whole thing is a constant for a given r, then we can take it out of the integral, and what we are left with inside the integral is ds. And the loop integral of ds would actually be the complete area of this sphere of radius r, which is given by 4 pi r square. And if you factor out the common terms here in the numerator and the denominator, what you obtain is q upon epsilon 0. So that's the proof of Gauss law. Now let's try to apply this Gauss law to find the electric field due to a uniformly charged infinite sheet. Now, for an infinite sheet, the field would be perpendicular to the plane of the sheet. So this can be seen easily here. We can just try this out. So if I have a sheet which is infinitely large, if I take a point here, and if I take another charge here, so you could see that at a given point, which is at a perpendicular distance from the sheet, the field due to this charge 1 and this is charge 2, field due to the charge 1 is in this direction, and field due to the charge 2 is in this direction if they are equally spaced from this central line, central point. And if you resolve these, then you get two contributions from these charges in the horizontal direction, which are in the same direction. And if you resolve this in the vertical direction, the vectors are opposite to each other and cancel out. Because this is a uniformly charged sheet, so the magnitudes of the charges are equal and they cancel out. So net field which is remaining is perpendicular to the plane of the sheet. And that can be seen here in this particular diagram. Now, to calculate the flux, we need a hypothetical surface according to the symmetry of the situation. So you could have a cylindrical pillbox or rectangular pillbox symmetrically protruding out from both sides of the sheet. So I have a cylindrical pillbox here with the flat area as A, the area of the base and area of the lid of the cylinder, that is equal to A, essentially this side, as you can see here. This is A and this is A, and the third is the curved surface. Now if you look at the direction of the field, if you look at this area, the top lid area, there the field is perpendicular to the area, and again sorry, they are in the same direction because the field is perpendicular to the plane, and the area normal is also perpendicular to the plane, so they are in the same direction, and the angle between field and the area is 0 degree, which means cos 0 is 1. So you just have E times A as the net flux across this area of the pillbox. Similarly, this side also the flux is E times A, and what we're left with is a curved surface. Now if you see in the curved surface, if you draw any kind of normal, then field would always be 90 degrees to the normal. Any kind of normal, the field is 90 degrees, so there the flux is 0. So there's no contribution from this lateral surface, the curved surface of the cylinder, to the flux. So the net flux is twice of EA, or E times 2A, and this should be equal to Q upon epsilon 0, and we are replacing Q as sigma A, where sigma is the surface charge density of the sheet, sigma A upon epsilon 0. So the net field due to this is given as E is equal to sigma upon 2 epsilon 0. So that's how you apply Gauss law to find the electric field due to an infinite uniformly charged sheet. Now there are a few more cases which you can do, which you can practice to apply Gauss law, and you could find out for a metallic sphere, for a dielectric sphere, non-conducting sphere. You could find out the electric field due to a spherical shell using Gauss law. All these applications they can be found on these links here given below, and in due course of time I'm going to be sharing these links with you, so you can go there and practice how to solve Gauss law. So that brings us to the next section, which is Ampere's law and displacement current. Now we all know that if a current carrying wire is observed, then you have a magnetic field around it, which is in form of concentric circles around it. And if I take a small element of this field, dl, then the line integral of this field would be b dot dl. And we also have the Ampere's law, which says that this should be equal to mu naught times the current threading through this loop, and mu naught is the permeability of free space. So this is the statement of Ampere law. The line integral of magnetic field around any closed loop is equal to mu naught times the net current flowing through that area enclosed by the loop. So that's Ampere's law. Now, if you apply Ampere's law to a capacitor, then there is a kind of paradox which happens there. So here we have the capacitor, and if I try to charge it using some kind of battery, okay, and I have a key here. Now this key is closed, then this plate starts getting charged, okay, and if you connect a galvanometer here, you would see a deflection in the galvanometer so long this plate is being charged. And if you put an ammeter here, connect an ammeter, you would definitely see some kind of current happening in the circuit. Now, the point is that there's nothing in between. There's a dielectric or vacuum in between, and still we register some current here during the charging process. So if we apply Ampere's law to this this whole situation, if you take a loop here, you can clearly see that this B dot dl is equal to mu naught I, because there's some current I flowing through this, and that can be measured here in this ammeter. But if you take a surface which is somewhat like this, then on one end of the loop you have the current going through, and the other there's nothing threading through this loop. So what you essentially get is zero. Now this is a paradox, how you could have current on one side and not on one side. So this breaks the continuity of the current. So Maxwell suggested that there is some kind of current happening here in this region also, which is responsible for the magnetic field that is found in this region, and that current is called displacement current. It's not a physical current in that sense. It's due to the change in electric field. So long the electric field is changing, you would have displacement current. You can actually calculate that too, which is given here in this formula. Displacement current equals epsilon times rate of change of electric flux. And the key takeaway here is that this would only exist if the field is varying with time. So this is the idea here. Now, so with that, we are done with this particular session, and having slight differences between, not slight, the major differences between the conventional current and the displacement current would be taken care of in subsequent lectures. I'll see you then. Thank you.